Before attempting to learn about Lenz's law, let us first recapitulate about the right-hand grip rule applied to a current-carrying coil. Consider a right-hand fist with the thumb extending out. If the fingers are wrapped in a circle pointing in the direction of the current through the coil, then the thumb points towards the end of the coil, indicating the north pole. Lenz's law helps us in identifying the polarity of the induced EMF in a coil. Lenz's law states that the polarity of induced EMF in a closed loop is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. We can put this statement in simple terms. If a current is induced by an increasing flux, it will weaken the original flux. If a current is induced by a decreasing flux, it will strengthen the original flux. The magnitude of the induced EMF is given by Faraday's law, which is E is equal to minus d phi b divided by dt, where E is the induced EMF in the coil and phi b is the magnetic flux. The negative sign in this equation represents the effect as stated in Lenz's law. Let us look at Faraday's experiments and apply Lenz's law to them. To identify the polarity of the induced EMF and the direction of induced current in the coil. In this experiment, the coil, which is connected to a galvanometer, is at rest. A bar magnet with its north pole facing the coil is moved towards the coil. This causes the magnetic flux through the coil to increase. A current is induced in the coil which opposes this increase in flux. The induced current is in a counterclockwise direction, looking from the bar magnet side. This current produces a north polarity towards the north pole of the magnet and opposes the motion of the magnet, thereby opposing the increase in magnetic flux through the coil. A force is required to move the magnet against this repelling force. The same magnet, when moved away from the stationary coil, causes the magnetic flux through the coil to decrease. A current is induced in the coil which opposes this decrease in flux. The induced current is in a clockwise direction looking from the bar magnet side. This current produces a south polarity towards the north pole of the receding magnet. This south pole attracts the north pole of the bar magnet, thereby resisting the motion of the magnet. When the south pole of the magnet is towards the coil and it is moved towards the coil, a south polarity is induced near the south pole of the magnet. When the same magnet is moved away from the coil, a north polarity is induced near the south pole.